If you have, if you have any question, please message me on this. What do you call this Teams platform? You can individually send me chat message if you don't want your message to be seen by others. So please communicate. See, the problem with the remote instruction is that I may feel that, oh, I am doing a really good job at teaching and everything, but it may not be effective for the students. So please, if you have any problem with, like, if you're not if you're not able to understand and so on, please do communicate. Okay, so let's get started with the class. Any question? Oops. Where did my... Okay, here it is. Okay, so last time I was actually showing these examples of Bremstrolling emission in astrophysical systems, and I wanted to annotate. So I figured out that the best way of annotating would be to actually put these graphs in the notes itself. So basically I've actually done that. So I will actually quickly again describe what I was trying to describe last time. So so if you recall that, it's almost good to sort of commit these things to memory, in the sense that, like, the emissivity due to free emission on a log plot from a single temperature thermal non-relativistic plasma sort of looks like this. Okay, so it has an exponential cutoff at h nu of order kt, where T is the plasma temperature, and this is a very weak slope. This comes from the Gaunt factor, this GFF, which is a function of h nu by kt, right? So it is actually useful to just even memorize these, because these things are quite useful. If you have an intuitive understanding of this is useful. Now this is JNU emissivity. What's shown here are two clusters. So I was actually giving examples of real systems which show Bremstrolling emission. So this is not energy per unit time per unit. This is not energy flux. This is the number flux. So for number flux, n nu, for example, should be proportional to J nu divided by the energy of the photon. So then this should have a slope of nu to the -1, right? At small frequencies. Is it clear? So we want to check whether this graph indeed has a slope of -1. So how would the slope, this is a log plot. So how would the slope of -1 look like? So this is 1 decade in energy, which is same as frequency. So basically a slope like this is what you expect, but you can actually see that this is somewhat steeper than that, right? And so basically what you expect is, like, this is sort of the exponential cutoff. So I've actually not drawn it perfectly. This is an exponential cutoff, but it's not as steep as I have drawn there. It's sort of somewhat shallower. So this is exponential cutoff, but this is not perfectly nu to the -1, right? Why do you think that this can be the case? Remember, this is for a single temperature plasma, right? So can someone make a guess or try to figure this out for me? So J nu is proportional to the -h nu by kt, and there is a t to the -1/2, right? If you recall the temperature and frequency dependence, and there's a Gaunt factor which we can actually ignore, which also has a h nu by kt, but it's a very weak dependence. So let me give you, so what I'm saying is this is somewhat steeper than this. u to the minus 1. Let me give you a hint. Clusters are not perfectly isothermal. If I draw a temperature profile for a cluster, it typically looks like this. So, it's, for example, at the center it can be 1 keV, and at the maximum it can be, say 5 keV or something like this. So it's not like perfectly isothermal. Now, does this give you some hint? This combined with this, does this give you some hint? No, yes, maybe. Okay, so let me tell you what's happening. So basically, if there is a range of temperatures, so these different shells will have slightly different temperatures. So what you will do is you will add up Bremstrolling due to this temperature, Bremstrolling due to this temperature shell due to this, and what you actually have, because of this variation in temperature, you're basically doing something like this. So you have like this. So a higher temperature one. So this is a lower temperature, right? And say 1 keV is this guy. So this is exactly that for 1 keV. Now if you have say 2 keV, so the volume, so it's sort of a, it's also proportional to the volume. So if you have a higher temperature gas, it would go something like this. If you have slightly even higher, it would go like this. So what happens is this shallow part becomes steeper because of the combination of different temperatures. So you see, this is the added, this is the sum. So it's not as flat as this single temperature graph. Do you get a qualitative understanding of this? And this exponential cutoff really happens at the hottest temperature, because these exponentials are sort of hidden by radiation from the hotter plasma. So the real exponential is sort of sensitive, cutoff is sensitive to the hottest gas, whereas this part is dominated by coolest gas. Why is that? Because emissivity goes like T to the minus 1/2. Right? It also depends on the volume of the plasma, but if we assume that all these guys have similar volumes, then it goes like T to the minus 1/2. Is this clear? Hello.
A bit, sir.
Somewhat.
Yes, sir. It's due to the factor of the relation between exponential and T. That's
Yes. So basically, this is a model spectrum for a single temperature. So basically, you have a plasma which has a constant temperature, right? So this is the model's spectrum that you get. But if you have like a range of temperatures, then you have to add these up, right? So the spectrum that you will observe is basically J nu at a given temperature times volume of the plasma, or dV. So 1 by V dV, so something like this. This is like a J nu from the whole volume, but temperature changes. So you have to add these up, and you can actually do it mathematically, right? If you recall the Bremstrolling derivation, we started with a single velocity and a single impact parameter, right? The first calculation we did, we had a single electron interacting with a proton, and we calculate we calculate
three plots you have drawn in this this red one at
yes.
different. So this is for single variation of means you are saying that there is variation of temperature
That's right.
in
So
the star cluster.
that's correct. So what you can actually do is, suppose there are 3 temperature zones, this, and this. Okay, so this is like a temperature profile. Okay, so this is the inner zone, middle zone, and the outer zone. Okay, and then you say what is the emission due to, if you consider this to be a single temperature like this to be a single, rather than a continuum. If you think about them as steps, then you can actually add up these 3 curves, right? And you can calculate the volume and add up. So the point I'm trying to make is that just because this does not look perfectly like this doesn't mean Bremstrolling. This is only for a single temperature plasma, right? So it comes close, but it's not perfect match. So what you do most of the time, what people do is they actually create a model profile and then sort of add them all together and then match with the observation. Which is this, sorry, not that. That's just a single temperature prediction. So that's why this is slightly steeper than u to the -1 that's expected. Okay, so this is this. Any question? So basically, even here you can actually think about, right? So you see, if you have combination like this is like a single temperature, this is like a single temperature, but when you add them up, it gives a steeper power law than u to the -1. Okay, so this is for galaxy clusters. Now this is actually, so one other thing that we have to be extremely careful about is that here we are assuming optically thin, right? So when you're optically thin, what you see is J nu dV, right? Your luminosity or your flux is proportional to emissivity times the volume. But so this is only true for optically thin. If it is optically thick, then at those frequency it should be black body, right? So if you go to very low frequencies where it becomes optically thick, this curve becomes like nu square. Why does it become nu square? Can someone tell me? So this is transition from thin to thick. Can someone tell me why this nu square would come? Recall, when you become optically thin, you emit like a, what is the magic word? You emit like a
Black body.
black body.
Black body.
This is the Rayleigh jeans part of a black body, right? So at low frequencies, I will actually show that at low frequencies, the absorption coefficient is very high for free emission and absorption. So here you become optically thick. So this part you only see when you're optically thin. That is, you can see through the emission processes, right? If you recall our chapter 1, anything that's optically thick is black body, and you cannot tell anything about the detailed process which produces radiation, because the photons that were produced have been absorbed and emitted so many times that all the micro physics of the emission process has been sort of wiped out and has been overwritten by this black body radiation. Okay, so indeed the galaxy clusters are optically thin, so you do see this nice Bremstrolling. Otherwise you would have sort of seen something like this, right? So this is nu square divided by nu, so nu to the +1. Okay, right. So the other thing that I also want to caution you about is, we consider this process, right? You have an electron moving, getting accelerated by this proton. So you see, where is the acceleration vector, right? So it sort of looks like this, and this is mostly where acceleration happens. So you recall that electric field is in the direction, is proportional to, in fact, is in the direction of a perp, right? So if you're looking from here, what is the line of sight projection of the acceleration? So for example, in this case, most of the radiation will come out in this direction because acceleration is perpendicular to the line of sight. If you're sort of seeing from here, the maximum acceleration is along the line of sight. It's only the A perp which matters. So this line of sight will see less radiation. If you consider only one electron, but we are considering an ensemble of electron, you have electrons coming from all directions. So this directionality goes away when you sum over a bunch of electrons. The other thing that we are making an implicit assumption about is that we are adding up the intensities, right? We calculated emission due to a single electron and then added up the powers due to multiple electrons. So basically we are assuming that all electrons emit incoherently. Can someone explain to me what I mean by all electrons emit incoherently, and I am fine averaging the emission of individual electrons? And how does it differ from coherent emission, for example? Can someone sort of enlighten us about this? At least try to make a guess. So let me give you a hint, right? When we do these interference experiments, right, we say that if you have a source which is incoherent, then you don't get these nice interference pattern. What you get is like a, you know, just like a maximum power at the center and sort of reduced intensity away from the center. So now can someone tell us about what is meant here?
Sir, maybe we've used dipole approximation, and in that we have only considered sum over dipoles, and if we consider them as means there is certain phase difference, means that's not variable, means it's averaging like means there is two, means there is not a constant phase between two.
That is electrons. Absolutely correct. So basically what so was that Sachin? Who was that? Who answered this? Yes, good. So basically what I'm saying is this electron which is getting accelerated here, right, and another electron which is sort of, maybe even in the same direction, some other proton, right? This electron and this electron, there is no definitive phase relation between the radiation that comes out from here and from here. Okay, so these phases, if there was a definitive phase correction, then they would have interfered. We should have added the fields, right, as we do in interference, right? Light plus light can give you darkness and interference. That's because it's the electric fields that you're adding up. In case of incoherence, light plus light always gives you light. You can never have dark because you're adding the intensities. In the same way, if these electron acceleration and these electron accelerations do not have a fixed phase relationship between them, you should add powers rather than adding electric fields. And that is what is actually assumed in this whole formalism that we are doing. That is, the electrons can be considered sort of incoherent emitters. This is not always true, but in astrophysics this is most of the time true. And in fact we will actually be doing incoherent radiation in most of this course. So I just wanted to highlight this point, because if these guys are emitting coherently, then you should actually change your charge to n times q, right? If all these guys have zero, it's as if like you have n electrons emitting coherently. So your charge actually effectively you can increase by n. So coherent emission can actually be extremely large amplitude, but it's very, very rare that you see coherent emission. So the where you can have coherent emission in astrophysics are masers and pulsar radio emission, where you have charges which charge bunches are produced, and they are like so coherent. They have very nice regular collective motion on very big scales, and all those charges emit coherently. That's when you have to add electric fields rather than intensities. And when you add electric fields, then you're like in case of intensity, right? If this is intensity I and this is intensity I, the maximum intensity is 2I, whereas here you can actually get 4I at places, right? Because of addition of amplitudes. This is just two slits, but if you have like zillions of coherent emitters, the maximum intensity of light can be huge. It is larger by a factor of n if there are n emitters, n electrons. So I just want, this is sort of a digression, but it's important to realize that we are doing incoherent Bremstrolling, incoherent synchrotron, incoherent scattering in most of this course. Okay, good. So, and this is, yeah. Okay, let's see. And it actually is useful to commit to memory, or how does the synchrotron, how does the Bremstrolling emission emissivity look like? Because you will, it helps actually if you know these things on top of your head. Okay, now what about this graph? What is shown here is that in black you have 1 keV plasma, so temperature is 1 keV, and you sort of consider a plasma with 1 keV. So these are produced from some plasma cores. So there is, there are a lot of them. One of them is called APEC. It's very popular in astrophysics. There is something called Chianti in solar physics and so on. But the end point is that what these plasma cores do is, if you give it metallicity, temperature, and density, these plasma cores can actually give you what the emission spectrum would be. So this black line is produced by some plasma core. So it includes things like free emission, which is Bremstrolling, free bound transitions, and bound transitions. Bound transitions give rise to lines like these in green and black. So this is for 1 keV. We know that if you have a 1 keV plasma, J nu should look like this. On the same graph, if you have 3 keV plasma, which is in red here, it should, so how should the 3 keV plasma look like? So it should be a little lower, right? It should, so if you recall, so this is emission per unit volume. If you recall, there is T to the minus half factor here, and E to the minus h nu by kT, and then Gaunt factor we can actually ignore. It's a weak dependent. So if you see, this would be something like lower, and it will have a cutoff line. So you can actually see the continuum, this black continuum and the black continuum, right, the region where there are no lines is above the red continuum, and that's because of this emissivity being proportional to T to the minus 1/2. So the cooler plasma is more emissive, right? It produces more radiation, but its high temperature or high energy cutoff is at lower value. And the green one, of course, is 9 keV, so it's even lower. So so this is the model for the continuum. This does not include lines. This is just for free. Now these plasmas actually also calculate these lines, and at low temperatures, lines are common. And the reason is that things like oxygen. So can someone tell me what are the most abundant ions in the universe? Of course, there's hydrogen, helium. After this, do you have like a sense of which ions are very abundant in just general astrophysical systems? So hydrogen, helium, of course, are the most abundant. After that, I also don't know the exact order, but let me tell you: so oxygen, iron, neon, maybe silicon, mud, and so on. So basically, so the ions which are more abundant will be more there in number, and so if your O becomes totally ionized, so if you have O6, so O8, so all eight electrons are removed, so this becomes fully ionized. This will have no lines, right? So as you go to higher and higher temperature, more and more of these guys become ionized, and you don't, these lines become very rare. This is only for iron, which has 26 electrons. So this is sort of like hydrogen-like or helium-like iron that can give these lines. Is this clear? So now you understand the qualitative nature for this curve? Yes. Okay, good. So these are the three. So now this is another example. This is from a. So now we are actually going to astrophysical examples. So some of my classes will have elements from I'll just these spectra qualitatively mostly. So this is thermal dust emission. So if you have a O star, right? So the temperature of O stars is 10,000, tens of thousands of Kelvin. So, for example, 3 times 10 to the 4 Kelvin. It's much hotter than our sun, and it produces a lot of ionizing photons. So if you have a star here, it creates this ionization region around it. These are called H2 regions. So all the hydrogen is fully ionized inside it, or mostly ionized inside it, and outside it's neutral. It's in the ISM. So this is if it is a fully ionized plasma, it should emit free emission, right? And this has a temperature of 10 to the 4 Kelvin. This is called nebular emission, nebular phase. So nebular means that when there are a lot of atomic lines like H alpha, nitrogen 2, and so on. So this nitrogen 2 is singly ionized nitrogen. Do you know how these things are written? Like oxygen 6 means it's oxygen with 5 electrons removed. So 6 corresponds to 5 charge 5 plus. So N2 means N plus. Like neutral hydrogen means H1 is neutral hydrogen. So this is a little bit of jargon, but it's useful to know. There's nothing very profound about this. Okay, so this is 10 to the 4 Kelvin plasma, which should emit free. So how should its spectrum look like? So this is actually what they are saying, that this is free emission. So this is a model. So it should have a very weak slope, almost near to the zero, but there is a Gaunt factor which gives a slight, at about h nu of order kt, there should be an exponential cutoff. Let's see, where should this occur? Let's see. So 10 to the 4. So 10 to the minus 16 kb is 10 to the minus 16. T is 10 to the 4. H is 10 to the minus 27. 6 times. So this is new. This is where new cutoff should happen. Let's see. So this is 0.5. So this is equal to 5 times 10 to the 11. So 10 plus 4 is 14. Is that correct? Hertz. Yes. So right, this is gigahertz. So this is about 10 to the 15. No, 9 plus 3 is 12, 10 to the 12. So the cutoff is not seen because it actually happens at much higher frequency, somewhere here, right? So that's why you only are in the flat part of this, right? It's this portion that you're seeing, not this one. And why are you not seeing the higher frequency one? Because this region not only has this ionized gas, it also has a lot of dust outside it, and this dust, is heated by the radiation from the star. And it's just like planets have a thermal temperature depending on how far they are from the sun, these dust has that sort of a temperature. So this is like about few hundreds of Kelvin. So this is like nu squared, right? You can actually check the slope. This is nu squared slope, roughly, right? So this slope matches that. So this is just black body, nu squared, and then it should be exponentially cut off. So it's actually a good idea to have actually feel for these different emission mechanisms and where they are expected to occur in various astrophysical systems. Okay, so this is H2 region. Good. Yeah, this is what I wanted to be able to do last time, because if I'm not able to annotate, the explanation is not that good. Was this clear, the annotation and the combination of these figures? No, yes, maybe. Okay, good. So now we'll go to the next class, which is this one. Oops, this should go away. So, any question on Bremstrolling emission? Now we will actually talk about absorption a little bit. So it was so again, to repeat, we were doing incoherent, non-relativistic thermal plasma most of the time. What about so whenever you have emission, what is Kirchhoff's law? Free absorption. What does Kirchhoff's law say? Can someone say? Can someone speak and say what Kirchhoff's law is? A good thermal emitter is also a good absorber, right? This is Kirchhoff's law in words, and in equations this is basically, it has a microscopic form and a macroscopic form. So the macroscopic form is alpha nu equals J nu by B nu, right? This is what your Kirchhoff's law says in terms of macroscopic coefficients alpha, emissivity, and this is right. Recall B nu is your I nu for black body, which is, can someone tell me? Maybe let's see if you remember. Right, this is the way I remember it. So this is the degeneracy factor. This is energy. This is sort of, I also remember it by, I know that e to the h nu by kt minus 1, and low frequency is just kt by h nu. And I also know that in the Rayleigh genes part, B nu should be twice kt by lambda squared. So, it's useful to even have this committed to memory, because you can always go and look in the books, but sometimes you want to like quickly estimate something, and you may you may run into something else before you're able to check. So it's good to know these things. Okay, let's see. Right, so now what did we do? We actually calculated J nu, right? We calculated this, the nu dV, right? And J nu is emission per unit volume, per unit frequency, per unit time. And I think it also has a per unit solid angle, because J nu was the mean intensity. Okay, yeah, so this is equal to 4 pi J nu. And as I mentioned, free emission, when you integrate over all the electrons, is expected to be isotropic, because you're considering all sort of orientations of electron ion collisions. So you just divide it by 4 pi, which is total solid angle. So J nu is per unit solid angle, and this is just overall solid angles. Okay, so let's see. Let me see. Okay. So what was this? Let me just rewrite what this was. 2 to the 5. I mean, this you don't have to memorize at all. Don't memorize the numbers and so on. Just memorize the dependencies on frequency and temperature. That's quite useful. Pi. I'm just writing it out from my notes. 2 pi by k m. This m is 2 pi by 3 km. This m is the electron mass, k is Boltzmann constant. half t to the minus a half z squared ne and I. And so this is important, this is important, this is very important. E to the minus h nu by kt. This is also important that at high frequency there's an exponential cutoff, and then this Gaunt factor, which is not that important too. No, because this is order unity. Okay, so this is your power per unit frequency per unit volume. So your J nu, let me just write it as J nu is equal to, rather than this guy, I should write 1 by 4 pi. So 1 by 4 pi, so this pi gets away, and this becomes 2 to the 3 rather than 2 to the 5. Okay, so this is your J nu. So now we can actually calculate alpha nu. We know our B nu as well. So alpha nu, so this is free, right? So alpha nu free is equal to, it's just J nu free divided by B nu. So what does it give you? Okay, so you just have to divide this by this guy, B nu. Let me just write down what I get. So 4 e to the 6 by 3 m hc 2 pi by 3 km. This is all fine. T to the minus 1 half z squared ne and I. Okay. Now we have nu to the minus 3 because of this nu cube in B nu. And so the ratio of this and right, so this becomes so this 1 by e to the h nu by kt comes to the numerator, so you have 1 minus e to the minus h nu by kt. This is this one, and then there's a Gaunt factor, of course. Okay, I think I have it right. This h comes from this guy, so I think this is fine. So the most important thing again is to remember the temperature dependence, the density, and this is ion charge. Most of the time Z is 1 for astrophysics, right? Most of the ions are protons, so you don't have to bother much about it. But you can also use these expressions for the lab, and if you have, say, a metal on which you are sort of shooting electrons and there is free emission produced at the boundary, you can actually use these formula with whatever Z you want. And this is the frequency dependence. So these are actually important. So you can actually see here, right? Low frequency has a larger alpha nu, and that's mainly coming from this factor, right? Nu squared. Okay. So we can actually just talk about the Rayleigh Jeans regime. Rayleigh Jeans regime is h nu by kt much less than 1. In that regime, alpha nu Rayleigh Jeans free is proportional to t to the minus a half z squared ne and I. So this, when h nu by kt is small, so this becomes h nu by kt. So this becomes nu to the minus 2. And there is t, so there is 1 by t, so this becomes t to the minus 3 halves. So let me actually correct that. T to the minus 3 halves. Okay, so this, so what does it mean? So suppose you have like a plasma, okay, and so now you are actually interested in knowing at what frequency does it become optically thick. What do you want to do? So it has a length scale L, right? What do? You say alpha nu L is order unity, right? This is optical depth. When my optical depth becomes order unity, my object will become optically thick, and at frequency below that, I will have a black body spectrum. So, and you have this expression for alpha nu. The numbers are actually given in the book. In fact, let me just, since I'm writing it here, so let me just write this again. This is 3.7 times 10 to the 8 t to the minus a half z squared ne and I nu to the minus 3 1 minus e to the minus h nu by kt gff bar. So this is the numerical value. And what are the units of this? What is the unit of alpha? Nu. Right, if you recall, di nu ds is equal to minus alpha nu is plus j nu. So what is the unit of alpha nu? I nu, sorry.
Alpha is length inverse.
My length. So this should be centimeter inverse. I think this is in CGS units. Let me actually check the book. It does not write the unit, but I think it is. Oh yeah, he says it's in CGS units, so it's centimeter inverse. Okay. So see, the course has elements which go back and forth. So you cannot, you cannot afford to just lose all the radiative transfer, because there is a relation between. So there's a whole program that we are following. Like, for example, in all radiation mechanisms, we'll perhaps use Kirchhoff's law to estimate absorption. So it's important to have intuitive and qualitative feel for these concepts. Okay, so this is, yeah, this is this. So now, as I was saying, for galaxy clusters, right, you see this, almost see like a exponential part here. But if you go to a low enough frequency, which is really, really low, then you should have this, if this is, say, flux observed as a function of frequency, this is like h nu order kt. This, can someone sort of tell me a procedure to estimate this break frequency? If I see a break at low frequencies for this free emitting plasma, how would I calculate new break? So
maybe derivation. You can derivate alpha nu.
Right. This is what you would use. What you'll say is that at new break, alpha nu break times the length of the column, basically the size of the plasma, should become 1, right? So now you have this expression for alpha nu, right? You have this expression for alpha nu. You say that this times length is equal to 1. So you can actually, what you get is, let me ignore all these numbers, but t to the minus a half z squared ne ni new break to minus 3, and let's say it's in the Rayleigh Jeans regime, which it is in, so this becomes h nu by kt, and let's ignore the Gaunt factor. This is 1, right? Times length, sorry, times the size of this plasma is 1. If you do that, you will get new break to the minus 2 is proportional to, so new break goes on the other side, actually. It's proportional to L t to the minus half z squared ne ni t to the minus 3 half. Right. So this is my new break. So what it means is that if I have a larger column, if I have a bigger, bigger size of the plasma, my break frequency is at higher frequency, right? If everything else is the same, Ne, Ni, Z, and T, if I have bigger and bigger volume, then my break frequency should go to larger value, like L to the 1/2. So this is the effect of making your volume or the size of the emission bigger. Similarly, if I reduce, so if my temperature is low temperature means more, right? Low temperature plasma emits very efficiently from Bremstrolling. It also absorbs efficiently. So the low temperature means that it will go, if your temperature is low, nu B is high. So it again goes to, sorry, if you're right, so if your T is small, this is big, nu B is high. So making your temperature low has the same effect as increasing your size of the column. So this is how you get it. Anyway, see, there is a close connection between radiative transfer and the observed spectrum. So this feature, I mean, this is very generic, right? At low frequencies, most of the emission mechanisms become optically thick at low frequencies before at high, earlier than at high frequencies, because absorption is more efficient at low frequencies. Okay, so you don't have to bother too much about the formulae, because formulae are easily available in the standard text. What you have to worry about or keep in mind a little bit is the mechanism and these dependencies on frequencies and temperature and so on. Okay, so I think we are done with Bremstrolling. So emission, absorption, these are aspects of the same. Emission and absorption are intimately related by Kirchhoff's law. So you can there are things like relativistic Bremstrolling and so on, but we will actually not cover it. It's not very common. Relativistic Bremstrolling means that the electrons are relativistic. The electron temperature is higher than 0.5 MeV, right? 0.5 MeV is the rest mass of an electron. So if your temperature is higher than around 5 times 10 to the 9 Kelvin, that's when you have to worry about relativistic effects. But most of the astrophysical plasmas that we deal with are non-relativistically hot, like galaxy clusters and H2 regions. Okay, so let me then start with synchrotron emission. Synchrotron emission is another very, very fundamental emission process. So December. Okay, let's get started with that. Oops. Oh. Okay. So synchrotron emission. Okay, so what is synchrotron emission? Right. So let me actually give you why this is important first. So magnetic fields are everywhere in the universe, right? The sun has magnetic fields, the interstellar medium has magnetic fields. Almost all astrophysical bodies have magnetic fields in them. Now, if you have magnetic fields, right, if you have magnetic fields and if you have charges, right, say electrons, these charges go around the magnetic field in this gyration motion, right? And when you have charge going around in the magnetic field, it's sort of like, it's a helical motion, but it's a circular the simplest one is when your parallel velocity parallel to the field line is 0, then you have a circular motion, right? So suppose magnetic field comes out of the plane, this is B, and so what particle is this? Is it an electron or an ion or a proton? I mean, I've drawn it going in the anti-clockwise in the anti-clockwise direction? Is it an ion or a proton? Can someone tell me? See, the electron and ion will go in the opposite direction. That's clear.
Electron.
This is an electron, right? B is in the Z direction. Q is minus E. This is the charge of an electron. V is in the phi direction. So this is your Lorentz force. Q cross B. So phi Z is R by Z. So it's R hat. So this is a force which acts in the direction minus R hat. So this is a centripetal force. This is a force which must act towards the center. Otherwise, otherwise it will not be able to produce centripetal acceleration. So this is an electron. A proton, on the other hand, would go clockwise. This is a proton. Right? You see the logic, right? For example, when you have a stone going around, supported by the tension in the thread, the tension force has to pull the stone inwards, right? So that it can have this centripetal acceleration that's always there when you have circular motion. So the force, whatever it is, Lorentz force or tension force or gravitational force, always must act towards the center. Got it? So this is an electron, that's a proton. This is the way to tell. The force has to act towards the center in all cases in circular motion. Okay, so let's see. So synchrotron motion. So you can have circular motion for electrons. Again, we'll deal mostly with electrons because protons are not as radiative, because for the same force, acceleration of electrons is much bigger than acceleration of protons, because they are 2000 times more light. They're 2000 times lighter than protons. So if you have V much less than C, speed of light, then this is called cyclotron emission or radiation. So in this case, what happens is, when V is much less than C, you can actually think of, so you have like circular motion and the electron is slow. So you can actually think of it as consisting of two dipole motions which have a phase difference of pi by 2 relative to each other. This is like the exam problem where I gave you an electric field which was circularly polarized, right? And if you have an electron which is non-relativistic, which goes, which is accelerated by this, this is not electric field, this is the motion of the electron. The electric field is sort of doing this, it's sort of, right? So, the magnetic, the electron in this case will also go in a circular trajectory, and you can actually think of it as this dipole in X direction and this dipole in the Y direction, and you just can add these two dipole radiations with appropriate phase, and you get the answer, right? In fact, the answer that you'll get will be identical to the question that I had in the exam, right? If you look from here, right, you will not see this, the electric field due to this motion, because n hat is along, the acceleration is along n hat, so you only see this. So you see linearly polarized light here. Similarly, here you see linearly polarized light, but from out of the plane, you will see both the polarization and you'll see circular polarization, because you see both this acceleration, it's perpendicular to n hat, and this is perpendicular to n hat. So this is called cyclotron emission. And cyclotron emission is just like a simple application of dipole radiation. Okay, what is synchrotron emission? When we sort of tends to see, you know, in fact, we will do ultra relativistic electrons in most of these things. So that means, you know, your gamma factor, which is 1 minus beta squared minus a half, is actually much bigger than 1. So your electrons are almost traveling at speed, approaching the speed of light. And this actually situation is very, very common. So, you know, you have AGN jets emit synchrotron radiation, where electrons have gammas of order 10 to the 3, more than 10 to the 3. And I mean, they're all, just as all the objects in the universe are magnetized, almost all the objects in the universe also have relativistic particles, relativistic electrons, which emit synchrotron emission, mostly seen in radio waveband, hundreds of megahertz to gigahertz. Okay, let's yeah. So this is called synchrotron radiation. When the particles radiation, when the emitting particles are relativistic. So in that case, the nature of emission changes in a very fundamental way, right? If you recall our discussion that if you have a charge which is emitting like this, right? So if you have, this is like the dipole beam pattern. If you have a charge which is which has an acceleration in this direction, right? It emits this dipole pattern. Now, if this charge moves very fast, say in this direction, perpendicular, so this is acceleration and this is velocity of the particle. So acceleration is perpendicular to velocity. So this is just like in circular motion. Velocity is in this direction, acceleration is perpendicular to that. So what happens in this case? So this is in the particle rest frame. In the lab frame, because of this beaming, all the radiation becomes forward beamed in a very small angle, which is of order 1 by gamma, right? So because of this fast moving particles, the nature of this, you know, like nice harmonic dipole, simple dipole nature of cyclotron emission totally changes when speed approaches speed of light, because of these beaming effects, sort of beaming and sort of Doppler effects change the nature of this emission totally in the lab frame, of course. Okay, let's actually get started with equations now. Let's see, what is equation of motion? Equation of motion of a charge q in presence of magnetic field, right? So and we'll do the relativistic case. So d dt of gamma mv, this is the rate of change of momentum. I mean, it has this gamma factor, very important, because as you approach the speed of light, your mass becomes heavier, and that's that gamma is equal to q by c v cross b. The Lorentz force, this expression for Lorentz force is correct relativistically. So v is the particle velocity, b is the externally imposed magnetic field, q is the charge, and so on. Okay, so this is this. So, and in, you know, I mean, in general, we should have this. But we are taking electric field to be 0, because, you know, electrostatic fields are very quickly shorted by charges. So so this, you know, you don't have DC electric fields present in most of the plasmas. So this is a good assumption that you can take electric field to be 0. in the lab frame. So let's see. So so what about this? So V dot. This is equal to V dot of this. So this is nothing but Q V dot E. And if we take electric field to be 0, this is 0. And the left hand side actually can be, I think there was a homework problem on this. This can be actually written as d dt of gamma mc squared. Right? There was a homework problem on this. I think Shipra also solved it in the tutorial session, right? Okay, so basically this is what we get. What it means is that in this circular like motion, gamma of the particle will be constant, right? And what is gamma? Gamma, oops, just a second. Right, so right, gamma is equal to 1 over 1 minus v squared by c squared. And if gamma is a constant, v, absolute value of the velocity, is equal to constant, or speed is constant. Okay. Right. So so what about this equation? We can actually write this equation in two parts. We can actually write this equation for, so if gamma is a constant, this gamma can come out of d by dt. So we have gamma m dv dt equals, I mean, the other way of looking at it is through energy principle. If you have magnetic fields, the magnetic force is always perpendicular to the velocity of the particle. So magnetic fields do not do any work on charges. So if they don't do any work on charges, the energy of the charges should also not change. So that's why gamma is a constant. So this is equal to Q by C V cross B. So if we let's actually decompose V. V is equal to V parallel Z hat. Let's assume, so B is along Z hat. Like without loss of generality, we can choose our Z coordinate along the direction of B. And there's a V perp which is in the XY plane. So gamma m dV parallel dt is equal to, how does V parallel change? 0, right? Because V hat, B hat dot V cross B is 0, because B hat is perpendicular to this. So what it means is that V parallel, the velocity with which charges are moving along the field lines, is equal to constant. Now if V parallel is constant, the magnitude of V perp is also a constant, because V, the whole V is constant. V is nothing but, which is V parallel squared plus V perp squared, square root of that, right? If V is a constant, V parallel is a constant, V perp is also a constant. But V perp changes direction, right? We know that, the perpendicular velocity goes around in a circle, so it must change direction. Okay. So we have gamma m dV perp dt is equal to, or let me actually write it in a slightly different form. Q by gamma mc V perp cross B And because V parallel cross B is 0 anyway. So this is this. And the magnitude of V perp is a constant. So this just describes this circular motion mathematically. And what does the motion look like? Right, so this motion corresponds to circular motion. And what is the frequency of that circular motion? So omega b is that frequency. So this is the frequency or angular frequency, angular of circular motion. This is equal to QB by gamma MC. This just comes from this. So this is dV perp dt equals omega b V perp cross z hat. So you can even solve it component wise and see that this is indeed circular motion. Right, so this is like a frequency. So this electron which is going around in the phi hat direction completes one circle in 2 pi by omega b. This is the time period of this is called a Larmor orbit, the circular orbit around a constant magnetic field, and this is called gyro frequency. This is called gyro because it's gyrating. Cyclotron gyro frequency. Okay. So this is useful to actually know. The easy way to sort of understand is also that this mass becomes heavier to gamma m, right? When the particle moves fast, its mass effectively become more and more. So that's what has happened. So mass goes to gamma m if your gamma is greater than 1. Okay. So the motion, actually, I already showed. Motion in presence of magnetic field is this helical motion, which is a combination of the circular motion in the perpendicular plane and a constant speed or constant velocity motion along the direction of field lines. And this can move either up or down. It depends on its initial conditions, for example. Okay. So it's useful to define something called, so this is like the V perp velocity, and this is like your V parallel velocity, which is along the direction of magnetic field, and this is your net velocity. See, V parallel is a constant vector, but V perp changes direction. So this velocity this velocity vector actually will sort of trace a circle like this, right? It will sort of precess as the particle is going around its circular orbit, but this angle will stay the same. This angle will stay the same, and that angle is called alpha, which is called pitch angle. This is just like these are just the standard terms that are used here. So if pitch angle is 0, what does that mean? A 0 pitch angle, what does that mean? Can someone tell me? Zero pitch angle means that V perp is zero. So you're just sort of zipping along the magnetic field. Pitch angle of 90° means that you have a circular motion and no motion along the field lines. Okay. And if velocity is V, so then V parallel is equal to V cos alpha and V perp. The magnitude of V perp is V sine alpha. Of course, V perp vector changes as the particle goes around in the circle. So this is pitch angle. Good. Okay, so what's the time? Okay, so let me mention one more thing and then we'll end the class. So which is one more thing. This is power. Total radiated power for synchrotron emission is, right? So we know that, right, we derived this Larmor formula is 2/3 E squared A squared by C cube, but this was only valid in particle rest frame. I mean, basically average rest frame. But here in synchrotron emission, we are considering the particle to move relativistically fast. But we had also derived, right, Larmor power is a relativistic invariant, right? So what we had actually done is we had written this acceleration measured in the instantaneous rest frame of the particle in terms of the acceleration measured in the lab frame, if you recall. And this was equal to 2/3. I'm actually using E and Q interchangeably, but let me retain Q because it is applicable generally. So Q square, and it's also consistent with the book, E square by C cube. If you recall, when we did this, so this was actually A prime. A prime is the particle rest frame acceleration, but we can write it as gamma to the 4 A perp square plus gamma square A parallel square. So we can actually write it in terms of the same thing. This is a Lorentz invariant, so the value of this thing evaluated in any frame will be the same, but we can write it in terms of acceleration in lab frame, in which these charges are moving very, very fast, relativistically fast. Here, what is A parallel and A perp? A parallel is the acceleration. So this is acceleration perpendicular to the particle velocity. And this is acceleration parallel to the particle velocity, right? You know, this parallel and perpendicular here in this expression is relative to the velocity of the particle. So for Larmor motion, for circular motion in this helix, particle velocity, right, is in this direction, and acceleration is centripetal. Acceleration is pointing towards the center. So acceleration, right? So A parallel. So A parallel is 0, right? You know, there is no acceleration. Just a second. So if you have a circular motion, of course, you know, acceleration and velocity are perpendicular to each other. So right, so we can just ignore this. So what we have is power is equal to, I mean, and we always want to write it in the lab frame because that's the frame in which we measure quantities. So this is equal to 2/3 q squared by c cube gamma to the 4. What is a perp? A perp is nothing but omega b squared, omega squared times r, basically omega. Right, so let's see, where is our equation? This is a per, right, so this is dv dt, this is a perp. And this is a parallel. So what is the magnitude of a perp? Omega b v perp, because v perp and z are perpendicular, so that's the magnitude. So a perp, so an a parallel is 0, that's why we set this to 0. So this is a perp squared, so 2/3, right, so this is your formula. And right, so, and recall omega b, this should really be, by heart to you, because it's very useful, right? It's just EB by gamma MC. So this is called the cyclotron frequency. So this is the power. This is the total power emitted by a particle which goes in circles around magnetic fields of strength B. We can actually write all these in slightly different forms. We can write it as 2/3 RE squared C beta perp squared gamma squared B squared. This is a different form, right? You see omega b square has 1 by gamma squared. So there's gamma to the 4 and 1 by gamma squared gives you gamma squared. What is Re? The classical radius of the electron. Again, I'm saying we can actually make it Rq just to have it general. So this is E squared by mc squared. This is the classical size of the particle. So q squared by mc squared. So this is another form of it. Okay, so again, we have to actually see these dependencies. This gamma square, b squared, dependence of total synchrotron power. It's useful to keep in mind because everything else is like a fundamental constant, and this beta perp squared. Okay, beta perp square is nothing but v perp square by c squared. Okay, so this is the total power. Now, if your electrons have isotropic velocity distribution, so what does that mean? So you have this direction of magnetic field, the z-hat direction. You have electrons with all sort of possible angles relative to this. It's isotropic. So if you have isotropic distribution, what is the average power? Angle average power. What is that? That's nothing but 2 by 3 RQ squared C. Gamma is a constant, so it sort of comes out of this. So gamma squared B squared and beta perp squared. So this you have to average all angles. What is that? That's nothing but beta squared 1 by 4 pi. I'm sort of doing an angular average, sine squared alpha d omega. Right, so this is the pitch angle alpha of this. This is the angle between the velocity and the magnetic field direction. So this is nothing but this guy is nothing but d cos alpha. Right, this is a standard integral And we also know another way of doing it, that like cos squared theta is 1/3 and sine squared theta average is 2/3, because cos squared theta is like z squared, which is 1/3 of r squared. So this is nothing but 2/3 of beta squared, right? If you assume isotropic distribution of pitch angles, isotropic pitch angle distribution, that's what you get. So this is integrated over all angles between electrons and magnetic fields. So your total power, that total average power, is equal to, so this 2/3 will give you sort of 4/3. Let me just write down sigma Tc beta squared gamma squared UB. This is actually a very, very useful form to commit to memory, actually. So this is the synchrotron power, total synchrotron power for isotropic distribution of electrons with velocity v and plasma, with beta, v by c of beta. So you see, what is UB? UB is magnetic energy densities, B squared by 8 pi. And I said that there is a background magnetic field UB. So this form is actually quite nice, because it's sort of like 4 by 3 sigma T C UB times beta squared gamma squared. So this is like sigma, so this is like N, so this is energy density, which is energy per unit volume. This is like flux of energy density. This is sort of like a so this is area, this is sigma T, right? Thomson scattering cross section. Again, we express everything in terms of Thomson scattering cross section. I think this is correct. So this is energy per unit volume, area times velocity. So this is like energy per unit time, E dot. So it's sort of like, N sigma V is like flux of particles. This is sort of like flux of energy, right? Where energy is contained by magnetic fields. So this is E dot, and then there is an extra gamma squared beta square factor. Normally beta is 1, so it's essentially gamma square. So 4/3 UB sigma Tc times beta squared gamma. It has a nice interpretation, right? Just like N sigma V is like N dot. This is sort of like collision frequency. This is like a collision frequency. In the same way, this is like collision frequency, but it's related to energy. Sorry, sigma V is collision frequency, N is not. So this is collision frequency times density is something per unit volume per unit time. This is centimeter cube per second. This is per centimeter cube. This is collision frequency. So number of collisions per unit time. So this is energy per unit time. So this has a nice interpretation like this. Okay, so this is actually very important. So this is very important. This is very important. It's actually useful to even commit these to memory. So also remember the path that we followed. Okay, it's actually, we are putting together very simple things like circular motion, this gyro frequency, just the Larmor power evaluated in the lab frame when acceleration is perpendicular to the direction of motion. Okay, so I will actually stop sharing and stop recording. So we are done with today's class. Any questions? Okay, I guess